Elements like oxygen and carbon dioxide are imperative to the survival of all living organisms. They nourish them, thus their name nutrients. These nutrients flow from the abiotic to the biotic and back to the abiotic components of the ecosystem in a cyclic path. This flow is termed as the biogeochemical cycle. There are two types of biogeochemical cycles. First is the gaseous cycle, whose main source of nutrients are the atmosphere and the oceans. The other is the sedimentary cycle, whose nutrients come from the soil, rocks, and minerals. Common among all biogeochemical cycles are three factors: input, internal cycling, and output. Input is the concept of bringing nutrients into the ecosystem where they are made available for consumption by plants and animals and decomposition by microorganisms in internal cycling. Then, these nutrients exit the ecosystem as the output. Nutrients enter the ecosystem in various ways. Those with the gaseous cycle are brought to the ecosystem through the atmosphere, while those with the sedimentary cycle enter due to the effect of weathering. Others enter by means of precipitation termed as the wet fall, and via airborne particles called the dry fall. Snow and animal activity also contribute to nutrient input. Moreover, there are through falls wherein, as it rains in the forest, the rainwater collected on the canopy drops onto the forest floor, and stem flow, in which rainwater from the treetop flows down the stems to the ground. Both processes involve water carrying with it the nutrients present as dust on the leaves of the tree. In aquatic ecosystems, however, nutrient inputs come from the surrounding land body and precipitation. In rivers and streams, nutrients come from the dead organic matter at watersheds. In every system, as elements come, elements must also go, and so these two components of the cycle counterbalance each other. Output can occur in several ways as well. Some plants and microorganisms convert nutrients into gas for immediate release, while carbon dioxide is transferred to the atmosphere via respiration. Flowing water on the surface of rivers and streams also transport nutrients from one ecosystem to another. In addition, animals like herbivores take part in nutrient output by consuming plants and depositing their feces into the ecosystem. However, there are nutrients that are removed from the ecosystems for good. This is possible through farming and logging, wherein the biomass taken away carry with it the nutrients. Furthermore, natural catastrophes like fire, leaching, and erosion contribute to nutrient output.
As said before, the nutrients of the world are kept circulating by the biogeochemical cycles. These cycles span multiple ecosystems due to the fact that the output of one ecosystem is the input of another and vice versa. Biogeochemical cycles can also work globally, as is the case with the gaseous cycle, whose main pools of nutrients come from the atmosphere and the ocean. One such gaseous cycle is the carbon cycle. We get our carbon from the carbon dioxide in the air and from the waters of the earth. It enters the food chain through the photosynthesis of plants, which are then eaten by herbivores, who are then eaten by carnivores. Carbon is released back into the air as carbon dioxide, and primary producers and consumers respire. A similar cycle occurs in aquatic environments, although they employ different organisms. The ecological niches are still the same. The rate at which carbon cycles through an ecosystem is determined by environmental conditions such as temperature and precipitation. In warm and wet ecosystems such as tropical rainforests, the carbon cycles rapidly due to high rates of production and decomposition. In cool and dry ecosystems, on the other hand, carbon cycles slower due to low temperatures, which in turn slows the rate of decomposition, allowing for the accumulation of dead organic matter. In ecosystems where dead material falls into the water, like in swamps and marshes, organic matter does not decompose completely and carbon circulates slowly. The flow of carbon can vary daily and also seasonally. In forests, the carbon cycling can vary depending on the time of day. In the morning, photosynthesis starts and the carbon concentration begins to decline. By afternoon, photosynthesis slows down due to increasing temperatures and decreasing humidity. This leads to an increase in carbon concentration. By sunset, photosynthesis stops completely and respiration increases, allowing the concentration of carbon to reach its peak. The carbon cycles also vary seasonally in relation to temperatures and the timing of the growing and dormant seasons. The concentration of carbon declines during the growing season due to the plants waking up and consuming carbon dioxide from the atmosphere. The concentration then rises as the growing season ends due to the cessation of photosynthesis.
Earth contains about 100 million gigaton of carbon. In the global carbon cycle, the carbon pool, which includes fossil fuels, aquatic biosphere, terrestrial biosphere, and atmosphere, is involved in contributing an estimated 55,000 gigaton of carbon in the cycle. It is the aquatic biosphere that accounts for most of the active carbon pool of about 39,000 gigaton, followed by fossil fuels with 10,000 gigaton, then by terrestrial biosphere contributing an estimated 2,100 gigaton, and lastly, the atmosphere holds about 760 gigaton of carbon. Carbon cycle happens both in aquatic and terrestrial ecosystem. In the ocean, surface water acts as a main site of carbon exchange between atmosphere and ocean. The ability of surface water to take up carbon dioxide is because of the interaction between carbon dioxide and carbonate ion to form bicarbonate. In terrestrial ecosystem, they are able to uptake carbon dioxide from the atmosphere through the process of photosynthesis. Aside from carbon, nitrogen is another gas that constitutes the Earth's atmosphere. It contributes about 80% in the atmosphere, and due to plants' inability to uptake it, there are two pathways for it to enter the ecosystem. The first pathway is during wetfall, as rain, snow, or even cloud and fog droplet, and during dryfall as aerosols and particulates. In the second pathway, via nitrogen fixation. Nitrogen fixation comes about in two ways, either through high-energy fixation such as cosmic radiation, meteorite trails, and lightning. They have enough energy to combine oxygen and hydrogen of water, thus resulting into ammonia and nitrates, which are carried by rainwater and assimilated by plants. The other way is through biological fixation, which is accomplished through symbiotic bacteria such as free-living aerobic bacteria and cyanobacteria, living in mutualistic association with plants. In general, fixation splits nitrogen into two atoms of free nitrogen. These two atoms of free nitrogen are then combined with hydrogen to form ammonia. This process is accomplished through nitrogen-fixing bacteria associated with the root system of plants. Ammonium is one of the two chemical forms of nitrogen that is generally available and can be used directly by plants. This formation of ammonium is the result of ammonification that took place in the soil. Ammonification is another process of nitrogen cycle. It happens wherein decomposer organisms break down amino acids to produce ammonia. In some ecosystems, after the production of nitrate, many processes may take place, one of which is the process of denitrification, in which plants uptake nitrate and reduce it to gaseous nitrogen. Denitrification happens wherein a group of bacteria like Pseudomonas chemically reduces nitrate to nitrite and nitrogen, then return to the atmosphere. Aside from nitrogen fixation, ammonification, and denitrification, human activities also influence the global nitrogen cycle. It significantly affects nitrogen input in both terrestrial and aquatic ecosystem. Improper use of chemical fertilizers heavily disturbs the natural balance between nitrogen fixation and denitrification. Additionally, use of automobile exhaust and industrial high-temperature combustion adds nitrous oxide, nitric oxide, and nitrogen dioxide to the atmosphere. These oxides, especially nitrogen dioxide, is converted into ozone by ultraviolet light when it reaches the stratosphere. The production of ozone is very harmful to humans and can cause several health problems. Phosphorus cycle in aquatic ecosystem moves through three states, where phytoplankton, zooplankton, bacteria, and microbial grazers are involved in the cycle. The cycle starts with organic phosphate being taken up by phytoplankton. These phytoplankton are eaten up by zooplankton and detritus feeding organisms. Zooplankton excrete phosphorus, returning it in the cycle, and more than half of it is in the form of inorganic phosphate. These inorganic phosphates are taken up by phytoplankton, and the remaining phosphorus, which exists in organic compounds, are used by bacteria. Then, microbial grazers consume these bacteria and excrete the phosphate they ingested. Some excreted phosphates are deposited in shallow sediments and some in deep water. Among the major biogeochemical cycles, the global phosphorus cycle is one of the unique ones, wherein it has no significant atmospheric component. The rivers transport an approximately large or small amount to the oceans, where only 10% of this becomes available for net primary productivity and the remainder goes into sediments. Moreover, the large volume of water in the ocean contributes to the increase in concentration of phosphorus. Also, the turnover of organic phosphorus in surface waters, with majority of it taken up, decomposed, and mineralized. And in deep waters, organic phosphorus converted into inorganic soluble forms will still be unavailable to phytoplankton unless it will be transported by upwelling. Hence, on a geological timescale, uplifting and subsequent weathering will return this phosphorus to the active cycle.
Another cycle that contributes to our ecosystem is the sulfur cycle. The sulfur cycle has both sedimentary and gaseous phases. First is the long-term sedimentary phase. This happens when sulfur is tied up in inorganic and organic deposits released by weathering and decomposition, then these are carried to terrestrial ecosystems. On the other hand, the gaseous phase of the cycle permits sulfur circulation on a global scale. What are the different sources that sulfur enters our atmosphere? Some of the sources are combustion of fossil fuels, volcanic eruptions, exchange at the surface of the oceans, and gases released through decomposition. But how do these sources enter the atmosphere? It enters the atmosphere initially as hydrogen sulfide, which quickly interacts with oxygen to form sulfur dioxide. Atmospheric sulfur dioxide is carried back to the surface in rainwater as weak sulfuric acid. This sulfur is then taken up by the plants and incorporated through a series of metabolic processes, starting with photosynthesis into sulfur-bearing amino acid. From the producers, sulfur in amino acid is transferred to consumer. Excretion and death carry sulfur from living material and back to the soil and to the bottom of ponds, lakes, and seas where bacteria release it as hydrogen sulfide or sulfate. One example is the colorless sulfur bacteria. This bacteria reduces hydrogen sulfide to elemental sulfur and oxidizes it to sulfuric acid. Other groups of bacteria, such as green and purple, in the presence of light, use hydrogen sulfide during photosynthesis. The purple bacteria are the best known bacteria which are found in salt marshes and in the mudfloods of estuaries. These organisms can transform hydrogen sulfide into sulfate, which is then recirculated and taken up by producers or used by bacteria that can further transform the sulfates. Lastly, the green bacteria can transform hydrogen sulfide into elemental sulfur. The atmosphere contains not only sulfur dioxide but also sulfate particles. These particles become part of their deposition, then the gaseous forms combine with moisture and are transported in precipitation.
The oceans are a large source of aerosols that contain sulfate. However, most are deposited in the oceans as precipitation and dry fall. The dominant sulfur gas emitted from freshwater wetlands and anoxic soils is hydrogen sulfide. Forest fires emit on the order of 3 times 10 to the 12 grams of sulfur annually. However, it is almost impossible to estimate the biological turnover of sulfur dioxide because of the complicated cycling within the biosphere. For the marine plants, their estimates of the net annual assignment of sulfur are of the order 130 times 10 to the 12 grams, while the addition of the anaerobic oxidation of organic matter brings the total to an estimated 200 times 10 to the 12 grams. Volcanic activity also contributes to the sulfur cycle. For example, the eruption of Mount Pinatubo in 1991 released on the order of 5 times 10 to the 12 to 10 times 10 to the 12 grams of sulfur. When this activity is averaged over a long period, the annual global flux is of the order 10 times 10 to the 12 grams of sulfur. We, humans, also play a dominant role in the biogeochemical cycle of sulfur. Therefore, the inputs resulting from industrial activity must be included.
The major source of oxygen is found in the atmosphere, and there are two sources for this atmospheric oxygen. One is through the breakup of water vapor through a process driven by sunlight. In this reaction, the water molecules are dissociated to form hydrogen and oxygen. The second source of oxygen is through the process of photosynthesis. Oxygen is produced by photosynthetic autotrophs such as green plants, algae, and photosynthetic bacteria. These autotrophs, along with heterotrophs, consume oxygen in the process of cellular respiration to help balance the amount of oxygen in the atmosphere. There are other reservoirs of oxygen, and an example would be water and carbon dioxide. They are the main reservoirs of oxygen, and all reservoirs such as these are linked through photosynthesis. Oxygen being so reactive makes its cycling in the ecosystem complex. It can be temporarily withdrawn from the circulation when it combines with other compounds to form various oxides. Atmospheric oxygen can also be reduced to ozone by high-energy ultraviolet radiation when oxygen is reconstituted into water during cellular respiration. Ozone is an important constituent of the atmospheric reservoir of oxygen. It is an ambivalent atmospheric gas which could be harmful when close to the ground, but helpful when it is in the stratosphere, which is around 10 to 40 kilometers above Earth. Although the major biogeochemical cycles were independently introduced, these major cycles are all linked in various ways. An example would be their linkage through their common membership in compounds that form an important component of their cycles. Generally, cycled nutrients are all components of living organisms and constituents of organic matter. Stoichiometric relationships among elements involved in processes related to carbon uptake and plant growth has an important influence on the cycling of nutrients in the ecosystem. These so-called stoichiometric relationships link the cycles of all essential nutrients needed for plant and animal growth.